All right. So we are going to talk about software-defined networking, SDN, thing that you have been waiting for. So first we will say what is SDN, what are the different alternative APIs, and this was the question asked before by somebody, somebody basically that what are the other APIs. We'll talk about those protocols, and then something else which is required for SDN, APIs and OSGi, and then the main thing which is the OpenDaylight controller. So origins of SDN. So SDN actually started with OpenFlow. OpenFlow guys came up with the idea of SDN. In fact, the person Masado who invented OpenFlow also invented SDN word. Nicira founded Nicira and then now sold it for $1 billion to VMware. So the idea was very natural to them because they said, look, once we have the OpenFlow, we can program the network any way we want, and so this is software-defined networking. Right? So initially, SDN meant that to do SDN, you have to separate the flow and the control and the data plane. You have to centralize the controller, and you have to use the OpenFlow. That was the definition of SDN. But now the definition has changed. That brings us to this cartoon. And everybody knows the story of 5 blind men and the elephant. Right? People from Asia certainly know it. And this is a very popular story. Actually, this is in my religion, they say that you could have many different points of view and all of them could be right, all of them could be wrong also, so it doesn't matter really. You shouldn't be arguing too much. So here is the thing. For some people, SDN is OpenFlow. For some people, it means that you should have something standard in the southbound. For some people, it means centralization of the control plane. For some means it is separation of control and data planes. However, the problem with all of these beliefs is that these are not really the framework. This is not really telling what you want. It just tells you how you should do it. What is your goal is not given by this. It just says go left, go right, go this way. Where you will reach, that is what we should be telling people. And then people can find their way to reach there. Right? So that's what happened in the last 2 years. First, people didn't know that, okay, well, with OpenFlow, where are we going to get? Can I get there by some other method? And so that is what has changed the definition. People are saying now that SDN is not a mechanism. These are all mechanisms, by the way. SDN is a goal. And how to reach that goal? So if you go today, there's a big debate in the industry about what is SDN. And if you go to one website, it will define it one way. If you go to another website, it will define another way. If you go to the source of everything called Open Networking Forum, ONF, this is the definition you will find. ONF defines SDN as the physical separation of network control plane from the forwarding plane, and where a control plane controls several objects and which is directly programmable, and abstracting the control from forwarding, centrally managing, programmably configured, and open standard-based, vendor-neutral program. These are the definitions of SDN. Now, problem with this is, with this definition, is that it includes how. First paragraph is all how, this is all how, and centrally managed is all how, this is all how. There doesn't really say what. All right? And so I'm going to tell you what it means, SDN, by defining what. So there are 10 things that you need, people that the industry needs right now. And these are the 10 things. First they need is virtualization. Doesn't matter how they get it. Whether they get it by OpenFlow or they get it by route flow or they get it by whatever we are going to discuss next. So the first thing they need is virtualization. Now virtualization doesn't say that this is how you do it. It just says that we need to be able to separate the physical from what I'm using. So I could have any number of routers, any number of processors, and I could create any number of routers, any number of processors out of that. right? So we need virtualization badly. We need orchestration. Orchestration means scaling. I should be able to move a band here and then 100 routers change at the same time, right? Programmability. Yeah, we need to be able to program. So, as opposed to, totally, changing the hardware. If we needed to change something previously, we need to bring a box in and connect it and all that. We don't need that anymore. We should be able to do all sitting in my chair. Dynamic scaling, should be able to change the size, quantity. Again, some of it comes from virtualization, some of it, more than virtualization. Automation is that basically we need to minimize the number of people. So as much as the machine can handle, better it is for us. So troubleshooting, finding the bugs, reducing downtime, policy enforcement, provisioning, reprovisioning, everything else should be somehow taken care of by some program and not by human being. And that basically reduces OPEX, operational expenses. Visibility, we should be able to see everything. Okay. Performance, we should be able to optimize the performance, plan the capacity, optimize the capacity, do the load balancing, fast failure handling. So basically, we should be able to do the performance. Multi-tenants, we should be able to share so that every tenant can do their own thing and their own addresses, topology, routing, security. Service integration, they should be able to put their load balancers, firewalls, IDS, wherever they want. It should be totally, in one word, it will be fluid. The network will be fluid. You can just move it any way you want. Open. And that is another important thing, is that people should have full choice of how they want to get it. So everything should be defined by what is called abstraction. What does abstraction mean? Abstract means, you write a paper, you write an abstract. That means that's the summary. That means the essence. That means the general idea of what this is all about. And then people can find out the details, work out the details. So we need to do abstraction. So the abstract is the opposite of concrete. Concrete is how. So when people are talking about abstraction, they should not be talking about how. They should be talking about one example of how, not the only example of how. Right? So, for example, we could say that find the shortest path from A to B and not say that, well, use OSPF. Yes, OSPF can give you shortest path from A to B, but that is how. Right? And so that is the definition of SDN. Based upon this, I wrote this down. This is a long paragraph, but since there are so many words that we need to get, I just couldn't write it shorter. SDN is a framework to allow network administrators to automatically and dynamically, and this is important, automatic and dynamic. Dynamic means very fast. Automatic means automatic, right? But it may not be fast. Manage and control both a large number of network devices and services. So it includes both devices and services. Important. Topology, paths, packet handling, quality of service using high-level languages and APIs. And the management includes provisioning, operating, monitoring, optimizing, and managing. Managing actually is very well defined as FCAPS in a multi-tenant environment. So this is trying to put all those 10 requirements into one paragraph, actually 2 sentences. And so the key is that it has to be dynamic, which means quick. The legacy approaches such as CLI were not quick. So we could program the network before. I mean, you had army of people who were sitting on the terminals, changing the routers, and they were writing command by command by command. But that was not quick. You ask them to change, something, and they will say, okay, it will take 1 hour. That's not SDN. All right. So legacy approaches such as CLI, command line interface, were not quick, particularly for large networks. So now, suddenly in the last 1 year, a number of APIs have appeared. For southbound, we have XMPP and 1PK. For northbound, we have I2RS, I2AX, ALTO. For overlay, we have, by the way, in this picture, remember, there is this overlay part, there is a switch part, there is a controller part, there is an application part, northbound, southbound. This is northbound, this is southbound, and there is overlay. All right. So for overlay, we have VXLAN, etc., etc. Configuration API, netconf, and controller APIs, PCE, and forces. Now, all of these are acronyms that you have not heard of, so I'm going to explain the most important of those. But these have been around or have suddenly come up in a new form. And so the industry is now totally, basically, in a big transformation where every organization is working on defining SDN in its own way. So IETF, Internet Engineering Task Force, is working on many of these words are coming from IETF. Open Networking Forum, obviously, is working on, many different ways. And so is ITU, and so is HC, and so is, every other organization that works on standards right now. So SDN is very ill-defined, and that is the problem. Right now, people are, somebody said this is a pure SDN, this is the correct SDN, that is the wrong SDN. So this is the same elephant story all over. People are fighting. I'm going to just describe some of the important protocols. Now, normally in a lecture on SDN, nobody will talk about some of these protocols because XMPP, ALTO, etc., these are not traditionally SDN stuff. SDN lecture goes 100% on open flow. The reason I'm talking about these protocols is because I have to talk to you about these. And since you are taking a networking class, you have not heard about these, possibly, because I had not heard about many of these myself. So I thought it is better to just explain all of these and then see how they fit in. XMPP. Actually, it was not designed for SDN. It was designed for messaging and presence. What is messaging and presence? When you do Skype, you are doing messaging and presence. When you log into Skype, everybody in the world knows that you are online. And then if they are your friend, they can talk to you. Right? Or there are other chat programs which do exactly the same thing, is that when you come online, your presence is told to everybody who needs to know. Right? And then once they know your presence, they can say, oh, I want to talk to you. That is the messaging part. All right? And messaging and presence is also, basically when you do, for example, texting. In texting, you have only one of the two. Which one do you have? Messaging only. There is no presence. I don't know whether you are on the phone or not. Right? And so there are many things. So basically, XM, X stands for extensible. X stands for XML. So there were many protocols before for messaging and presence, but XML makes them extensible. Basically, you can write whatever you want to, fields you want to add very easily with XML, right? It is similar to SMTP. What is SMTP? Transfer protocol. So that is the mail program. SMTP you use every day, right? SMTP server. So mail, but the mail is not presence. Mail does not tell you presence part. It does the messaging part again, right? But doesn't do the presence part. So XMPP does the presence. Basically, it tells you that the other guy is online and that, you get the response right away. So otherwise it is similar to the mail, except it is real-time mail. And each client has an ID which looks very similar to your email. So it could be jan@boostal.edu/mobile. So it just doesn't end with your email. It also has the device or whatever else you want to name. So for example, your phone. If you're on your phone, it will, that is how you will reach to it. Right? Client sets up a connection with the server. So there is a server, just like the mail, there is a mail server. Everybody sets up a connection with the server. And as soon as you do that, you have presence. And the server knows who you are friend with. Right? Because you have told them that these are my contacts. You told Skype, you told whatever the chat program. Let me see. What are the chat programs people use? Anybody? Huh? IRC. Yeah, IRC. Right. IRC. What else? Google Talk. Yeah, Google Talk is a chat program. And so, if you name, I'm sure Microsoft has something similar. What does Microsoft use? Huh? Oh, they bought Skype, yeah. So anyway, every company has presence software nowadays. So anyway, so the thing is servers, just remember, all of them are very similar. Basically, you declare your friends, and then when you come online, the friends know it. Basically, the server tells everybody. So that is the presence part. And the messaging part is when you send it, right away it is sent to the client. See, that's the part, is that it comes right away. The messages are pushed, so as opposed to the mail. Mail, if I don't check for the whole day, I don't get the mail. But in this case, the text comes to my phone anyway. Whether I check it or not, it is there, right? So it's kind of pushed. So that's the main difference as opposed to being pulled or pulled. All right. So this is XMPP basically came to IETF from another community called Jabber. And so Jabber was being used for chatting, and it was so successful, they said, let's make it a standard. And so they came to IETF, and so there is an RFC which describes all this. So all the messages are XML encoded. So this is called XMPP because all the messages are XML encoded. Okay. So basically, XML encoding makes it very extensible. You could add a new field to the messages, new things to the messages, whatever you want to do, right? The only thing wrong with it is that it is not very good for binary files because everything has to be converted into ASCII. So you have to do some kind of binary to ASCII conversion. And so generally people don't use it for binary file transfer. They use it out of band binary channels for those things. A number of open source implementations of XMPP are available. So if you wanted to use it, you just look for it and you can download it. Variations of it widely used, for example, in Google, Skype, Facebook, and many games. It is used in IoT. You haven't got into IoT, Internet of Things. So in Internet of Things, basically, and for data center management and so on and so forth, now it is being used. And I will show you in the next slide how do you use it in the data centers. But basically, the clients respond to your XMPP messages. So the summary is that the chat does not have to be with the people. You could chat with a machine. Machine could tell you that it is online. Machine could tell you that it is offline. You could tell the machine that please, start this, start that. So all of this suddenly came to people that, look, XMPP is here. Why do we need any other protocol? We can just use it to talk to machines, chatting with the machines. So Arista switches can be managed by XMPP. Juniper uses XMPP as the southbound protocol for SDN. All right. So let's see how it is done. The data center, everything, whether it is a VM, whether it is a vSwitch, whether it is a pSwitch, whether it is a personal physical machine, everything is an object, and every object has an XMPP listener in it, module in it, which basically connects to the server and says, look, I am on, tell me what to do, if you want to tell it. And it also says, who is my boss, who is my friend, who can send messages to me, who cannot send messages to me, just like you do on the chat. Okay, and you have complete management system. With complete security, isolation, everything else that you are looking for is already there. Okay, so this is the last slide on XMPP. Any question about XMPP? Yeah.
When we talk about SDN, we usually talk about programming switches or routers. But from your diagram, can you also program the hypervisor and the virtual machine?
No, the thing is, basically hypervisor may have some parameters that you can change.
Okay.
Like, for example, one message to the hypervisor would be start a new VM. Yeah.
So for the messaging part here, what kind of messages could be like sent to the, is there like, do they follow certain protocol for messaging between devices?
So protocol is XMPP, by the way. The question is what kind of protocol? So the protocol for messaging between the devices is XMPP. It is XML. So you could put any fields that you want in XML. Remember how XML works is that you define a schema somewhere and then the device will follow that schema and they will understand what this field is. Yeah.
Just one more question. With the, since this is a southbound API, can we mix and match? Can we use a southbound API from one vendor and one to another, or is that just a nightmare?
Right. So right now it is a nightmare. So the question is, I mean, one vendor could define. So the thing is, XML could be standardized. So we could have an industry standard schema for hypervisors, for example, and then everybody will use that schema, and then it will be all standardized. That step has not been taken yet. But that is going to happen very soon because, as you see in the next parts of the slides, things are moving very fast. All right. Second then is path computation element. Now again, this is pretty old. PCE, and the reason we have PCE is that when you do MPLS, and you tell the router MPLS that I want to set up a path to that destination, the router has to do computation, quite a bit of computation, to find a path that satisfies your requirement, which is that I want a 10 megabit path with so much latency, so it cannot go through Germany, and so on and so forth. So that requires a lot more work than a router can do. And not only that, sometimes you need two paths which do not overlap. So you want a primary path and you want a secondary path. So what these guys came up with a few years ago is called PCE, path computation element. They said somebody else can do the computation and tell me. Simple idea. So MPLS and GMPLS requires originating routers where the path starts, originating routers, to find paths that satisfy multiple constraints, including not using any of the backup routers and having a given bandwidth. So you could say that I don't want to go through these because I'm already using them. Right? So this requires more power than the routers may have. So PCE working group came up with a set of protocols, and there are lots of protocols, so which a computation client, PCC, the router, can use to get the path from the PCE element. Okay, so this is a little bit what say unintuitive. So when you say PCE, that means the server. Okay, instead of calling path computation server, which would have made it much easier for me, they call it path computation element. Okay, so PCE is the server and PCC is the client. So the client can say, here the client, it can say what is the 1 gigabit route to New York not going through Boston. All right, and PCE, which is the server, has a whole database. Using that database can come back with the answer.
Server would mean the controller in the network.
Server could be controller, yeah. So here's another thing. Let me just explain every time. Server is a function. Where you put it is your decision. Packaging, you can put it in the controller, you can put it in a separate box.
But controller has a responsibility of path calculation and populating the table.
In OpenFlow. Yeah, right. So this could be like a route flow where server could tell the controller and then controller could program it. Right? So anyway, so this is an element which does the control. And by the way, all of this is pre OpenFlow days, right? I mean, at that time there was no concept of controller. So the PC is the server and PCC is the client, and basically it just does the path computation. So in fact the standard allows both functions to be resident in the same box. So the router could be the client. It will just have two modules. The client module will ask this element module, please tell me the path, and the answer will come back right there locally. Right? They divided the path computation into two parts so that you can move the modules if you needed to, or you could have the modules only in some routers, like 4 routers could have the element and 100 routers could use it. Right? So they had basically you could have distributed or centralized. Centralization is not required. You could have totally distributed, you could have totally centralized, or you could have in between. There are 25 plus RFCs which describe all of this. All right, PCE. Any question about PCE? Yeah.
So now the path information that returned by the server might include the path that going to the other PCE.
No, hold on. So the PCEs don't have, unlike a controller or anything, PCEs don't have a control of a router. So they cannot say, well, you should not take this road because I don't own that road. So they will give you the path, and then somehow the other PCEs will discover that now that path is used and the bandwidth has reduced. So there is a database. So there is a protocol, PCE to PCE communication protocol and PCE to PCE protocol. So others will come to know that now that path is not available anymore, but there is no dedicated control. Yeah.
So this the router supporting this PCE is
Okay. The question is the router supporting this PCE is a reactive router as opposed to proactive router. So yes, basically, in the sense that you don't set up a 1 gigabit path unless you have a 1 gigabit dollars. I mean, these are very expensive paths. You go to the carrier and you say, I want this, link to the Boston. Now it will require a few signatures before it will get done, because these are very expensive paths. They are not just done on a whim. Reactive. You do it on demand. All right, so now you can see how PCE fits into this whole software-defined work, because now that PCE is pretty old. Actually, I forgot the year there, but this is there. Now people are saying, look, I can already program my routers to do this. Why don't I use this also along with OpenFlow? Then there is a forces. Forces is forwarding and control element separation, and this has been working since 2001. In 2001, IETF thought that we should separate the control from the forwarding plane. And so they have, each thing has two elements, control element and the forwarding element, and they have two managers, the control manager and the forwarding manager. Okay. And by the way, this is not one-to-one. So there are multiple lines going out of the control. So one element could control multiple forwarding elements. Okay. So the idea was, and then it was implemented in early 90s in BSDs, the control and data plane separation. But anyway, it allows the routing tables to be controlled by a simple command line or by a routing daemon. So basically, you could change the routing table by saying, we change routing from A to B by this method. Now, what it does support is, forces supports is port type, link speed, and IP addresses. So you could ask for these things by using forces. You could ask, what is your port type? What is your link speed? And you could set up some of these. For example, IP addresses could be set or asked. IPv4 or IPv6 unicast, multicast forwarding you could set. QoS, including metering, policing, shaping, queuing, etc., could be set. Packet classification could be set. So you could, just like OpenFlow, you could say, well, this kinds of packets to go this way or put into this queue and do that. High-touch functions, things that require modifying the packets, like network address translation and application level gateways. So everybody knows what is a NAT, right? You just change the address. Application level gateways are something that not only change the outside IP address, but also change the inside IP address. What is an inside IP address? Is that if you have a packet, it is going from A to B, it might have a message in which message says, well, I want you to do this from C to D or whatever it is, right? Now, those C to D could be IP addresses. And those addresses will not have a meaning if they get out of my network, right? So somehow we have to change those to a meaningful addresses such that they can get back to where C and D are. And so some gateways, application level gateways, they understand the application to that extent. They are just designed for that application. For example, application level gateway for FTP would be designed just for FTP. It can read all the FTP messages. It knows which messages have inside IP addresses. It will change them. Okay. So this allows that. Encryptions to be applied to the packet. It could say that please encrypt the packets before they send them out. Measurement and reporting of per flow traffic information. So Forces does many of the things that we have been talking about. Okay. So now this is coming back to life. Any question about Forces? Oh, actually there is one more slide on Forces. So this one simply shows how this works. So for example, first the forwarding element manager will come up and the control manager will come up, and the managers will exchange, will basically authorize each other, authenticate each other. So this one sends a security exchange message. After that, they authenticate each other and they say, okay, I like your certificate, you like my certificate. Then this will tell them what are the CEs that it's managing and what are their attributes. This will tell what are the FEs and so on and so forth. Now that the FE manager has the list of CE and FEs, and the CE manager has the list of CEs and FEs, they will talk to their managees or their employees, whatever you want to call them. So FE manager will talk to the FE and say, look, first they will exchange security exchange. So it's all secure, authenticated that you are talking to the right person. Then they will say, okay, tell me what is your ID and what are your attributes. And then you will say, okay, this is your controller, CE ID. So FE manager will tell FE that now your control you should take from this controller. All right. Similarly, the CE manager will tell CE that now you should talk to this FE. Right. So there are two bosses, and the employees listen to their boss only. So first, the bosses talk, and then the bosses talk to the employees. And then the FE and CE will do the same thing. They will security exchange. Then they will tell you what is the attribute, and then this will give you the configuration and routes, everything else that needs to be done from beginning to the end. Any question about Forces? So it's all straightforward. So now we go to ALTO. ALTO is application layer traffic optimization. I don't need to remind you that all of this work that we talked about so far in this lecture is all IETF. Internet Engineering Task Force, right? And so they are all working group in IETF. ALTO working group is working on totally different thing. Now they suddenly came back to SDN, and let me tell you how. So they are called application layer traffic optimization, and they are working on P2P traffic. They were working on optimizing P2P. All of us do P2P, and the problem with P2P currently is that you could be here and you could be talking to peers over there in Germany, and you're just wasting the network resources. If the carriers were a little bit more friendly to us, they would say, look, that is in Germany, why don't you talk to somebody in St. Louis? And that will save a lot of traffic to them and save a lot of time to us, right? And so that's what this group is working on. ALTO group is working on a way so that the service provider could tell the clients or the users where these people are located. What is their characteristics? How far they are? What is the link bandwidth they have? If I have more information about the peer, then I could more intelligently select the peer. Make sense? Right now, we just randomly select the peer. I mean, actually, we give a lecture on P2P in 473, and we tell you how it really selects using BitTorrent. But right now, I'm not going to go through that. So we just randomly select, and if somebody works out good, then we just hold on to them. If somebody doesn't out good, we move on to somebody else. So that is not very optimal. So ALTO group is designing so that you could do some better peer selection. And the way it does is that there's an ALTO server. ALTO server knows all about every node in the network, right? So has knowledge of the distributed resources. An ALTO client simply requests that please tell me about these peers. And then it tells them by either by topological distance or by traffic charges or something like that. So you could sort them out any way you like, just like you go to Amazon when you want to buy something, you sort them out in any order you want, highest price first, lowest price first, best reviews, so on and so forth. So you can do that. And then the ALTO server could get the information from the provider or from the nodes about their data characteristics. So either this ALTO server could belong to the AT&T or something and they could just give it to you. Or if they don't, then the peers could get together and say, okay, ALTO server, look, my bandwidth is so much, my this is so much, and so on and so forth. So they could do it by themselves. Client may get the list of the potential peers and send it to a server which can return an ordered list. Or the client could say, well, I have these 5 choices, which one is good? Tell me. Or which 5 or 4 are good, whatever. Also need a protocol for ALTO server discovery. So you need to find out where the server is. So there is a protocol for that. You need a protocol to talk to the server or get the responses back from the server. So all of this has been going on for quite some time. The question is, how does it apply to to SDN? All right. So the minute they heard about SDN, they said, yeah, we have the solution. And the solution is as follows. If you want to locate any resource in the data center, this is the most friendliest environment you can find for P2P. Actually, everybody is not only a peer, everybody is owned by you, so you know every resource, how much bandwidth they have, how they are connected, what is, things like that, right? So all this thing can be given to the ALTO server, which could be a single server in the data center, and it will have the cost information, it will have the constraint, it will have the power, etc., etc. And then the client gets the right place where to put their next, whatever they want to do. It could be a peer, it could be another VM they want to put. So you could get optimal location for your devices, for things, or, or optimal devices to connect, or optimal services to connect. If you want to connect to an IDS, you go to the ALTO server. And now the main thing is, which probably was not there in ALTO before, was the issue of privacy. Because P2P is such an open thing, they probably didn't think that, okay, some people you should not tell some things. Okay, so this client, I cannot tell you that this is, and for that client, I can tell you. So that kind of security has to be built in, which is not there right now. But it has, it has all the commands for finding the resources. All right. So now here is an application, and some people have already designed this application, that you could have an orchestrator which will talk to the ALTO client, which will control many data centers, and then the ALTO client will say which data center should I put my VM in, and then it will just find the right place and put it in. All right. So that is, we already learned about several of the alternatives for making the networks software defined. So what is happening in the industry? So the current debate in the industry is about what versus how. Previously, SDN was defined by how. Now people are defining by what, and then they're saying, you tell me what you want to do, and I will tell you how to do it. In 5 different ways I will tell you. So SDN is easy. So here's the thing. Do we need centralized control plane? The answer is no. PCE allows you to do the same thing without centralization, with distribution, with centralization, every possible way. So the centralized control plane makes it necessary. Centralized control plane it makes it easy, but not necessary. So the thing is, you have to distinguish the easy from necessary. Distributed solution may be required for legacy equipment or for fail-safe operation. So now let's see, how does the army run? Army, the way it runs is that the boss says run, everybody runs. Our boss says stop, everybody stops. But if the boss is not there, what happens? The soldier knows what to do. right? So that's what we need, is that we don't have to shut off the brain. We have to just use the brain as told up to whatever point it is told, and when the other person is not there, we should be able to run. And so that's the kind of the world which we are in right now. When we join a company, they don't take away our brain and say, okay, cut off your brain, and then now I have all the brain in one place. You leave your brain with you, and they just tell you, and you have to follow them. If you don't follow, they fire you. So that's the kind of real world situation it is right now. Complete removal of control plane may be harmful, in fact. As I said, exact region control plane between centralized and the distributed forward is yet to be worked out. And it's not really clear what should remain in the forwarding and what should remain here. Because there are certain things, which are too much intensive interaction. You don't want to put them in the central place. So just totally removing it is not a good idea. SDN is easy with a standard southbound protocol like OpenFlow, but one protocol may not work, as we have seen, because we saw 1.0 did not work for MPLS, then we put for MPLS, then we put for one IPv6, then we put for this, and then we will be doing it forever. Why not just take what is already existing? So diversity of protocols is a fact of life. There are no standard operating systems. It's like saying everybody should use Windows or everybody should use Linux. Nobody is going to listen to you, right? So that's the thing. There is no standard operating system. There are no standard processors. There are no standard routers, and there are no standard Ethernet switches. So you cannot just insist on one protocol. So if the industry finds an easier way to solve the same problem by another method, that method may win. For example, I spent myself 10 years in ATM. ATM's promise was quality of service and circuits. And people found a better way, MPLS. All right, MPLS won because MPLS required minimal changes to the routers, and they didn't require to throw away all your routers and just do. So that is what is happening right now in the industry, is people are trying to find out what is SDN and how we can do it. What are the alternatives? Okay, any question about that? By the way, none of this, much of this you may not find written, because a lot of this is, basically philosophy, thinking and all that, right? So SDN controller, if written today, and this is actually from this book, so that one is written, is that if written today would be much like this. First of all, you will have the overlay, you will have the network elements, then they will speak many protocols. Then there will be a layer which will somehow translate those protocols into a common language that the controller can think about. And then controller will have, in addition to doing the control, it will have something that will allow you to do the services such as slicing, topology, whatever the network services you have. It will have orchestration so that, you can manage thousands of devices at the same time. It will have management so you can monitor what is going on. And right now people are talking about two different kinds of things. First is the OSGi framework and one is the RESTful API. So this is the current thinking, and this can change any day. And the current thinking is, looks like the standard where you will have southbound protocols, plug-ins. So that is the word right now very hot, is that they are designing a controller which is general enough and anybody can put any protocol. So it's not limited to one protocol. You can plug in the protocol. So most of these things are plug-in. Everything here is a plug-in. You just plug in a controller, you plug in a service, you plug in a orchestrator. So you just modules. So they're defining the modules. And that's where this framework comes in, OSGi framework. And I'm going to explain that OSGi framework. Let's see. So I will start maybe REST a little bit for a few minutes and then you can take REST. So REST we have already talked about. REST is this web style interface, right? And the web style interface was done by a PhD thesis by Roy Fielding, and he studied many ways to interface things, and he found that the web is the right way to do. Web was already there, but he says that we should design everything like they have done for the web. So in the web, basically these are the things which are done, is that client and servers are there. The server is stateless. Server talks to thousands of clients, so it doesn't keep anything. All right, clients keep all the state. And the advantage of that is it becomes scalable. Now you can serve millions of clients and not worry about running out of space. And the responses can be cached for a specified time, just like in the web. and the intermediate servers proxies can respond. So all of these things he took from the web, and he says that every application should do this. So that is called REST, representational state transfer. There are only 4 instructions: create, read, update, and delete, CRUD. 4 operations, and in terms of web, we use them: get, post, put, and delete. So if you write HTTP, if you write HTTP, which we again teach in 473, very first day, HTTP, you know that there's a get, post, put, and delete. For any web page, you can do that. You can get the web page, you can write the web page, you can post into your form and all that. So that is what we should do with every application. So when you design an application which uses these commands, we call it REST API. Okay, and I will continue this next time because we run out of time. But basically, use the URL, right? You can say get this controller, this model, this and that, and you can get that. Okay, everything becomes like a web page. All right, we'll continue next time on Wednesday. Remember to come to 509C and bring 4 hard copies.